Hey everyone, as you guys know from the previous video, I'm Kartik, and right now we'll be going over part D of the Zelha tree problem. So, the Zelha tree problem tells us to describe an algorithm in English for building a Zelha tree. Sorry everyone who doesn't speak English. Yeah. Anyway, for full credit, your algorithm must take less than theta n squared time, and partial credit is still given to algorithms that complete it in theta n squared time. Now, it may be very tempting to try to jump into the algorithm that takes less than theta n squared time. After all, you want to get all that full credit, right? But before we do that, why don't we just start off with a more natural solution and try to work ourselves up to a less than theta n squared solution. So before we get any further, let's just make some function create Zelha tree. And it takes in some sort of list, right? Okay, now let's just think about what were our first steps when we were constructing a Zelha tree out of a list. Well, in both parts B and C, we first started out by finding the minimum element. So why don't we just let some sort of index, so let some index I be equal to the index of the minimum element in L. Of the minimum element in L. And now let's just let make some node. So tree node. Tree node. T is equal to Li. Okay. Now what do we do? So we have some sort of tree node, and so we pretty much just have the root of the tree right now. Where else can we go? So let's make an interesting observation now. The left child of 1 is 2, right? And 2 is also the smallest element in the sublist of everything before 1. Similarly, 5, 1's right child, is the smallest element in the sublist of everything after 1. So, because trees are a naturally recursive data structure, it may be nice to do something recursive here. So, we know that if we sort of think about this, if we have a sublist of there's 13, 7, and 2, if we call this same function on that list, then 2 would be the root. Similarly, if we had a sublist of just 5, 16, 8, and 9, and we call the recurrent function on that, then 5 would be the root. So why don't we just do t.left is equal to create Zelha tree of L from 0 to the ith index. Note this splicing does not include I. And we make t.right equal to create Zelha tree for everything after. So L I plus 1, and then to the end of the tree, which is just going to be, let's just call it n for now. It's just an algorithm after all. And what do we want to return? Well, we'll just want to return the tree node. So return t. And it may seem a bit magical, but just ponder on it for a little bit, and I'm 99% sure that you'll understand. Now, let's just check to make sure that this create Zelha tree actually works. So we first find the index of the minimum element here. So that's, we get the minimum element. That's 2 in this case. Then we do create Zelha tree for the left, and we set that equal to this. So we find the minimum element of everything on the left side. in that case, this would be 3. We find everything to the that's the minimum of that's left side, which is just going to be 9. Then we find the minimum of 3's right side, which is 6. Now we finally moved on to 2's right side. And the minimum element on that side would be 10. And the minimum element on his left side is non-existent because it's null. There's nothing in between 2 and 10. And then the minimum element on its right side is 14. Okay, so let's just check the min-heap property really quickly. 2 is less than 3, 2 is less than 10, 3 is less than 9, 3 is less than 6, and 10 is less than 14. So the min-heap property is good for this. It's good. Now let's check the in-order traversal. So we start off on the leftmost element, 9. We go to its parent, 3. We go to 3's right child, 6. Then we go to 2. We go to 10. We go to 14. Matches up perfectly with that list. Now, we know this zealotry works. So let's just try to find the running time of this. So in the worst case, you either have a list that is a recursive call which makes t.left every element besides the element that you just picked, or t.right is everything that you just is every element except for the one you just picked. In other words, say we had some like list like this, and then you had like, I don't know, like 100, 200, blah, blah, blah. So then what would happen is first we'd pick this element, and then there's nothing to the right of that. So all the recursive calls would go in here and create zealotry here. And then we go on this element. So finding the minimum of the first time would be theta n time. And then finding the minimum element of everything besides the first element would be n minus 1. And then if you keep doing this for n iterations, this becomes theta n squared time, which is still partial credit, which is still pretty good. Actually, that's what I did when I did this problem on my midterm, and it worked out pretty okay for me. But we can do better. So let's think about, let's actually just erase everything before we continue. So I hope your midterm studying is going pretty well. I know midterm studying can be stressful, but just be sure to eat like some fruits or something. Be healthy. Maybe have like a watermelon, papaya, a few grapes. Let's see what else. What other fruits are there? Bananas, oranges. I try to maximize my intake of fruits actually, and it's how I maintain my vibrant skin. Sorry. Okay. Now. Okay. Now let's think about what it means for there to be a theta n algorithm, because theta n is less than theta n squared. Theta n means that we want to do one pass of the entire array. Right? So we don't want to do anything besides one pass, which means that we want to construct our zealotry while we are just going through the array itself. Now, that seems a bit mystical, right? So how can we do this? Well, one idea is that we can keep building up to the root and building and have a few cases. So for example, if we know that something is going to be less than the root, then we know that it should be the new root. So before we jot down getting more ideas, let's just make some sort of function, create zealotry, like we did earlier. And again, it takes in a list of L. And we want to iterate over it. So for I to L dot length. Let me say I equals 0 to L length. What do we want to do? Well, as I said earlier, maybe I should put this a bit lower. Create zealotry. Anyway, So let's keep a variable root for now. And let's say for I equals 0 to L dot length. We wanted two cases. One, if Li is less than the current root, what do we want to do? Well, we know that everything that is like the root has necessarily come before Li in our list, which in turn means that it's come before it in the in-order traversal. What does that mean? It means that even if it's not the root anymore, it should still be on the left of Li, which means we should make Li dot left, assuming that we have some tree node for Li, is equal to the root. And then what do we want to do? We want to make the root equal to, oh no, what is this? Oh, the root is equal to Li. Perfect. So we have one case. That's fun, right? Now we have an else case. So the else case is if, in other words, Li is greater than or equal to the root. So what do we want to do? Well, we know that there are some cases where, like for example, it should come after everything that has already occurred, which means we should put it on the right of the last inserted element. So now it may seem that we need to actually keep track of another variable, which is last inserted. And what we want to do here is, okay, so if Li is greater than the last inserted element, what do we want to do? Well, that means that we want to make Li the right child of last inserted, because that means that it'll come after it in the in-order traversal, and also it's a bigger element, so it'll fulfill the min-heap property. But what if Li is less than last inserted? What do we want to do then? Well, if that's the case, then we won't want Li to be the parent, right? Well, it could be the parent actually, but we'd want last inserted to be to the left of Li. So we have to do some modifications. So to find Li's rightful place in the Zelha tree, we need to have a while loop. While, and we'll do while Li is actually less than last inserted, we'll make last inserted equal to the parent of, I'm going to call last inserted Li now. Parent of Li, just for space. Sorry about that. Now, what do we want to do once last inserted is less than Li? Less than or equal to, rather. Well, we know that last inserted comes necessarily before Li in the in-order traversal. And since it's less than Li, we know that it should be above it, which means that if last inserted is now here, we want Li to be its right child. Okay? But we have to remember that there could still be some right child for last inserted before Li comes around. So, like some node here. But we can't just do away with it because it's still in the list. So what we want to do is make sure that it comes before Li and after last inserted. For this to happen, we need to make Li dot left equal to the right child of, let me just close this thing off, last inserted. Then what we'll do is make last inserted dot right is equal to li. And that's about it. But before we are done with this entire thing, let's just do one thing that we don't have to do, that we have to do regardless if it's an if or else. We need to make last inserted, oh no, last inserted is equal to, what is it? The, li. And finally, we'll just return the, outside everything, we'll return root. I got a bit cluttered for space a bit towards the end, but hopefully that made sense. Now, let's just check to make sure that this works. So we start off with a root of 9, and then that's about it. Then we have the case where li is less than the root when we have 3. So that means that we make the new root 3. Okay. Then we have the case where li is actually greater than the root. So we go to the else case. And last inserted happens to be 3, so we don't go through the while loop. We make li.left, so 6.left is equal to the right child of last inserted, which is null in this case. So then we make last inserted.right equal to li. So 3's child is now 6. That's fine. Good. Now what we do is we have 2. 2 is less than the current root, which is 3. So we make 2 the new root, pretty much. Then we have 10. 10 is greater than last inserted. So that means we put a, we skip the while loop, and then we make li.left is equal to the right child of last inserted. Last inserted is 2. There is no right child of it, so we just make 10 the right child of last inserted. And then we follow the same process and we get 14. So that's it for Zelha tree, and yeah, have a good one. This problem was fairly challenging, so don't worry if you didn't get the full credit solution. But now you know.